this is my Redstone calculator, and where I am at currently on it. I'm not finished. I've got a division to do, which you guys are going to experience with me in a future video, I think. Maybe this one. I don't know. I haven't decided yet. So, first off, shout out to RecRap2. He got me wanting to do this project. Because calculators are really cool. Learn a lot. And shout out to Matt Batwings. Not that they need a shout out from me, but he helped me a lot with learning how to do this stuff. On his less his redstone calculator design, just his actual computational redstone. That was useful. But basically, these, what I'm standing in front of right now, these are gates. This is an AND gate, which means that this has to have both of these signals on to work. It does this by using these two redstone torches that powers this redstone torch. So this is off unless both of these are off. This is a NOT gate, so it just inverts the signal of the redstone torch. This is an OR gate, so if either of these or both of them are on, the redstone signal goes through. This is an XOR gate, most complicated. If one signal's on, it will go through. If both signals are on, it will not go through. This is used in a lot of things. XOR and AND are what are the basics for doing addition. So I'm going to walk you through the adder first, then the actual calculator, like typing, then subtraction, multiplication, and then we'll figure out addition. I think we can get on this. So, this is an adder. I have these two turned on right now. So, there's three signal inputs, the main two, and this is the C input, or side input. There is two outputs, there's the C output, and the main input. This, currently, is 1, this is 2 in binary, I should probably just do binary somewhere. So how binary works is, instead of our thing, it goes up in 1s, 10s, and 100s place. Binary goes up in 1s, 2s, 4s, 8s. So we go at 1, 10, 100, 1,000, 10,000. But this is a 1s place. So let's say we just have 1s place on. We have 1. Let's say we have 1 and a 2s place on. Then we have 2 and 1, which is 3. So this is 3 in binary. Let's say we have an 8. That's just 8, 9, 11, 15. Now, if you add all these up, you'll notice how 1 is 1 before 2. This is just 1 before this next digit, 3. This is 7. This is 15. So basically how this works is you can get every single number if you just multiply what each binary digit means by 2 every time. So this will be 32, this will be 16. So basically how this goes is it's 1s, 2s, 3s, 1, 2, 4, 8, 16, 32, 64. Oh, there's already signs at the back. But yeah. Then over here, an adder. So you'll notice, you might think, oh, this is 3. No, this is 1 and 1. Both of these are in the 1s place, so is this, but we don't have to worry about this for now. So 1, add 1, is 2, which is what we're getting as output. But how this works is you run both these signals through an XOR gate together, and through an AND gate together. So what this does, if both are on, then it's this. If one is on, then it's this. That is basically how this does math. Now, next bit's a bit complicated. You then have a C input. Now the C input is run into an XOR gate and an AND gate, but that is with this. So this is the original XOR gate. this gives an output, which is then run through an XOR gate with the C input, and an AND gate with the C input. So what that is if only one of them is on, then basically if one of them, those two is on and this one's on, it won't go through there, it'll go through there. If both of those are on, this signal won't be on, which means that this signal can then get to that one, which would then be 3. So it's not really doing math, which I find cool. This is a looped one. I'll find a better one since that one's a bit broken. That's a subtractor, we don't need to worry about that. So, this basically, how you loop them together to get obviously more addition would be nice, is you take the C output, or the 2's place in the original one, and you loop that into the C input of the next one. Now this works because obviously it's a carry. C stands for carry input and output, because what you're doing there is actually you're just adding 1 and 1, and there's a carried one, just as if you were to carry a 10 forward in the next bit. So what that does then is it then adds on the carry with the next inputs, which are then worth double the amount. So if I put this in binary, this is 3 in binary, obviously it gives 3, this is 1 in binary, so if you add 3 and 1, you should get 4, but you get 0. I didn't test this one actually. Oh, that makes sense, yeah. You get 4. I haven't used this one before. I used a different one last time. I'm a bit sick right now. That's why I sound unwell. But you know, I felt in the mood to make a YouTube video about my calculator. So that is how addition works. You loop multiple together. This is the same thing but vertical. So basically, C input is here, C output is here. So you just loop them together like that. And then binary obviously goes down the way. So, this is the calculator bar. This is where all the typing goes in. So this is basically what I have over there. So, you can type a 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So when you do, it takes an input. This was complicated. I just copied this bit actually, because I do not know how to get 9 inputs from something this close together. But yes, you take the input, you bring it around, and then you power 1 line of these. Only 1, because you don't need any more. And from there, this then also powers 1 up above, 2 more above technically, because we need. Never mind, that's wrong. I take it back. So let's just go for 1. So 1 powers this. This right here. This one. Nope. Where does 1 power? This one. Nope. It's complicated to go diving through your redstone. Actually, might be this one. No. Ah, who cares? Let's just find 1 here. So 1 is powering this, which then powers this down here. So it's this one. Why is there a redstone torch here? Oh yeah, this is the signal basically. Every single one powers this. So up top here we have the 4 binary inputs, because 4 is what you need to get up to 9, and we have a signal, which just shows that we have pressed a button basically, which will then be used to move it along. So in these 4, what you do is, since you pressed 1, and 1 is this line, in binary it's 1, 0, 0, 0. So all we do is we make it so 1 gets activated. There's just this one line, and then we get and the signal. Then we get an activation of 1, 0, 0, 0, and the signal input. And that is how you code stuff into binary. Now over here at the actual calculator, you'll see it's a bit more complicated. This wire, which does all that, with the signal input and a few more, just because I need a clear input and all that. But these are the basic 4. These then get split into 2 different wires because you have a top and a bottom. But what they do over here is signal input powers this, which temporarily unlocks these repeaters. Now a locked repeater just keeps a redstone charge, whether it's nothing or if it's positive. So what that does is it then lets this go through to the next layer. So if there's a 1 here, the 1 would then go here. If there was nothing here and there's a 5 coming through, a 5 would then be let through. So that is used to then basically make it, if you type a 1 then a 5, you get 15. But all the binary numbers just go in here and they go vertically. We have over here, this is a lever which is used to switch between the top and the bottom platform. So bottom obviously is because there's 2 rows in a calculator. So what this does is if there's a binary number here, right, I'll just type it in over here because it's easier. Currently I have 7 typed in actually, which is 0111. So let's analyze this one at a time. So there's a 1 here, so this should equal 1, which it does. That's 0. But how that works is there's a repeater going in here, which means this block is powered, which means that this is on. There is this, which soft powers this, which means the repeater can get power out, but it means this is off because nothing's powering it. Then this is powered, this is not, this is powered, this is not, this is powered, this is not, this is powered, this is not. So if there's a 1 signal in, that means that it physically cannot be a 0, a 2, a 4, a 6, an 8. And if there's a 2 power in, then basically it cannot be a 0, it cannot be a 1, it can be a 2, and it can be a 3, but it cannot be a 4 or a 5, because those are powered. It can be a, it can't be a 6, it can be a 6, yeah, it can be a 7, can't be an 8, and it can't be a 9, because there's no 2 in any of them. Same with 4's place, where it is only the ones that it can be. Same with 8's place. So what this does means that if there's a 2 on, that means that the 1 cancels out everything, or the redstone torches mean that since a 4 is not on, it's not going to be any of them, it's not going to be any of those 2 because of 8. It's not going to be anything that needs a 1, so that means the only one left that it could be is this, which is 2. So if you put those 2 together, they cancel everything but this one, which is 3. So how this then works from there is this is 1. It then loops down to here too, because we have this display over here. It's called a 7 segment display, as there's 1, 2, 3, 4, 5, 6, 7 segments. I'll show you 8 in a bit, just so you can see them all properly. But each of these segments is put into one line, and basically, if this is unpowered, these redstone torches then power the specific lines coded in just by these to make the specific segment needed. So if I put an 8 on, that's a 9 currently. 8, that means that this is unpowered. So these 2 are unpowered, which then means that it powers literally all of these lines, which then means each of these is powered. So that is how typing on a redstone calculator works. Quite complicated. Yeah, I have 9 of these, 3 on top, 3 on bottom, and the redstone locking system, which is very complicated. Took me a while to get that. Actually spent an hour and a half not being able to type an 8 or a 9 because one locked repeater was like that instead of like that, which was not very fun. I've spent about 48 hours on this project in game, not including just watching videos. So from there we then need to come over here. I already have 128 types, so let's go over here. So I actually didn't show off typing, did I? I should just do that now. This is the clear button, I think. Yeah, this is the switch lines. So if we type a 1, we get a 1. Type of 2, we get a 2. Type of 3, we then get a 3. So it's 123. Now you can switch rows. You can type whatever you want numbers wise. I did that too quickly actually. You can't do it too quickly. I'm gonna clear both. Yeah. So let's say what's an easy number? We'll do 2, 2, 2, 222. Now, addition works with a long binary number. Currently, we don't have a long binary number. We have a 2, a 2, and a 2. We need a 2, a 20, and a 200. So how we do that is, out of this first section here, this is just a 2. We take the binary out, the binary input out, and we get this 2. So we put this into an adder because that is the 2's place. This is the 1's place, 10's place. So we need this 2 to turn into a 20. So we take out this 2. It's just this layer below this. Turns into here. So we decode it back into the 1, 2, 3, 4, 5, 6, 7, 8, 9, obviously. So we get a 2 out here. And what this then means is the 2 then basically is then re-encoded, but this time into 20 instead of 2, which we then just add on to the 2. So now this is binary for 22. We then do the same with the 200s column, where we encode it to 200 instead of encoding it into 2, and we then add that on, so that this is binary for 222, which we can then use in future stuff like addition and subtraction. That took a while to do, and I could use vertical adder to make it more compact, but I kind of like how it looks. It looks kind of cool. So for example, I'm going to do a 1, a 2, and an 8. 128. Now 128 should just be one lamp one, which it is. So this is 128 in binary, which is wonderful. That's exactly what we want. This thing is just the exact same, except it also has the bottom layer done. Now this is my actual current one with my addition, subtraction, and multiplication. Because I can't re-download my Mac app. Ignore that. That doesn't work. So let's say we want to do addition, and I type 128. And we want to add on 128. Now this should get us 256. So here the signals come out. They get split into 4 different signals. It looks quite complicated, it's really not. This is the addition line. Say we're doing addition. So basically all this does is it lets out just the top, just the line that we want. Which is here, 128. And then this line then goes on into the big adder. And that adds up 128, add 128, which is 256. Which should be this bulb over here. Nope. We're gonna pretend that worked first. Yeah, which is 256. So, actually, I haven't checked if all these work. I really should. I don't do enough testing, really. That's gonna need to appear there. Oh, for Pete's sake. I test all the stuff individually, I don't really test them all together. Which is an issue, I should test them all together. So, yeah. Now, we're going to tackle subtraction. Which we have to come down here for, which I did a little bit of previously. This is how you do subtraction. We're just gonna ignore this bit for now. So we're just gonna do 101, this is 5, minus 011, 3. 5 minus 3. So the weird thing about subtraction is that you don't do it, you do addition. For some reason, if you invert this 3, so 100, and add 101, then you add these two together, which is 5 add 5, you then get this, which is 10, 1010. This is 10 in binary. But if we just ignore this input on the side here, you get 1010, which is 2. So to do subtraction, you invert what you're subtracting, add 1, and then you just add those two together, and you forget about the signal at the very end. This works if it's 000000011, 00000000101. There can be as many leading zeros as you want. It'll still just be the input furthest to the left would be on. So, as another example here, what did I even do here? I don't know. Oh yeah, other way around. 3 minus 5. So 3 minus 5, you would invert 5, which is 0, 1, 0, add 1, 0, 1, 1, add those two together, and you'd get 0, 1, 1, 0. Now you'll notice that this white number at their end is 0, 1. If it is that, all we have to do, since it's obviously 3 minus 5 isn't 6, obviously, you would invert this and add 1 again. So you get 0, 0, 1, add 1, 0, 1, 0, which is 2. But obviously 3 minus 5 isn't 2, it's minus 2. But if there's a 0 here, all that means is that this is a minus number. So how we do this is, since we already have an add 1 on the very far end here, the C input, that we just keep that on and we invert one of the signals. And what is this current equation? I think it's 3 minus 5 actually. Is it? 3 minus 2? No, it is 3 minus 5, yeah. Which is giving us 2 currently. But, yeah, so 3 minus 5. So we have 2 inputs that go into this. We have this input, which goes into this, and we have this input, which also goes into this. So, currently, since we're getting a minus number, this very far left one isn't powered, which means that this is powered, which means that then makes sure that this signal doesn't go through, but this signal does go through. So all that does is it makes it so the answer is 2, as opposed to whatever the other answer would be. And since that far one is on, we can just use that to power a minus symbol. Now if I were to reverse this, this is 2 columns, so I'm actually doing both of them on still. Let's say 5 minus 3, right? Those two actually need to be on. Nope. Is that 5? That's 6. That is 5. That's 5 minus 3. Which gives us 2. But if we go over, okay. I'm kind of fumbling right now. So yeah, I see what I did wrong. That should be 5 minus 3, which is 2. So 5 minus 3 is 2, which means if we come over here, this final input is powered, which means that over here, we do not let the input from this second subtractor go through. We take it from the first subtractor, which then means that we have 2. But since this is off, this means we don't have a minus symbol. So this is just regular old 2. Hello. I was just rewatching the video and I realised I didn't explain subtraction very well. So basically, what this is it inverts one of the signals as you're meant to do, and this is the C input, which just had 1. There's always that. And then what I do is I take the output and I put it out here, but then I also take the output and I put it into another inverter and add 1 up here, which is what the second one is. So basically it chooses whether it inverts and adds 1 twice or once. I didn't explain that very well. So up here I have my subtractor, which is very nice, all hooked up. It works, I think, last time I checked. I haven't checked in a while, if I'm being honest. Speaking about not checking in a while, these need to be inverted signals. So these should all be on. This is what happens when you don't do enough of your calculating. This is 0 minus 0, which is 0. With that, yeah. Oh man, I hate being sick. So, that's my multiplication. Yeah. So, I'm gonna take you over to the multiplier. This is the multiplier. So, how does multiplication work? Basically, this 0, 1, 1, 1, 7, 1, 0, 1, 0 is 10. So 7 times by 10. What we do is much like regular multiplication. If you had like 23 times by 5, you do, or 23 times by 56, you'd do 23 times by 50, and 23 times by 6. So what we have here is basically 4 different rows. So these 4 rows, they signify this bottom number. As you can see, 1, 0, 1, 0. But every single row, you would multiply it by 10. So if all of these were on, it would look like this. So every single row, you don't multiply by 10. You just change this out. So you move it up 1 more column. So this is not the correct answer. This would be 7 times by 15. But then what you do is you see these ones here, on signal. This is on, off signal. You get rid of them. On signal, off signal. So what that does, these by the way, these are just 7. Move along. You then get 7 times by 10, which this is 70. So if I go over to this actual machine, this is 7 times by 11. What this does is it's a bunch of adders hooked together. So what this does, so this bit right here, this moves the binary number up 1 place every single number it moves along. It goes up 1 binary place. So that's basically just what happens over there. And then these numbers, if they're on, they let the signal through. If they're off, they don't let the signal through, which is also what I did over there with the ones that are off. They're in full black wool. So what this is 7 times by 11. So here you have 7. Here you have, this is moved up 1 more place, which is 15. Should be. No, 14. This is 14. This is 7. It just times it by 2, actually, does it? Wait. No, it doesn't. That's just pure coincidence. since it's moved at one brain place, 14, 7. You add these two together, you get 21 over there. This signal is off, so we just forget about that one. This signal is 56 right here. So this one right here, 56. So then take 56, you add it on to nothing because that one was turned off. You then add on 56 and 21 in this one. This final adder is just to add on that, or it's add on that bit, and then this final one's add on that bit. But you get 77, which is this. So how this works, it's literally just vertical adders chained together. So those two are added together, 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 those two are added together. Then all the adders in the middle are just to make sure they're all added together properly. And then, yeah, I mean, that is pretty simple, I think. It's just used for multiplication. It looks really complicated though, which I like, because it makes me seem smarter. Now, if I should go inspector mode for this. So all I have here is my multiplication hooked up. So this basically is controlling these inputs here. Yeah, bottom input, this is top input. That's just what these redstone torches do. They just put them in, and that's how you get the multiplication to work. Now, I have not done division yet, so instead of watching me explain it, we're gonna figure that out together in another video. Yippee! Oh, I shouldn't have broken that, because I do not want to do division in this video. That is too complicated. It deserves its own of me struggling. And also, I'll then put the output as well in that video, but that might take a while to come out. It has been like a year since my last upload. Not because I've been doing this. I mean, kind of, but also not only. But yeah. Oh, I didn't even show you how the clear button works. The clear just basically lets all the repeaters unlock for a long time. But yeah. Au revoir.